In today's lecture, we will be discussing about the quantum state estimation. We are still in the qubit subspace. So we will start with a state of a qubit, and we will see how to estimate a state of this qubit. So mathematically, we know a state of a qubit psi, the canonical representation we wrote last time, which was cos of theta over 2 and sine of theta over 2 exponential of I phi. That's the most general representation for a qubit psi, state of a qubit psi, where theta is between 0 and pi, and phi is between 0 and 2 pi. This is just to remove the degeneracy that we know two values of theta and phi should not result in the same state psi. That's why this restriction is there. They will be evident, or they will be clear later on when we discuss more about the state representation in the geometric form and in other forms. It will be more clear why we are taking it in this restricted subspace. But this is also easy to find, whether when we allow the full range of theta and full range of phi from 0 to 2 pi for both, then there will be two values of theta which will give us the same state. So we don't want that because of overload phase. So we start with this thing, and now we see mathematically, or the first postulate of quantum mechanics tells us that a state of a quantum system, mathematical structure, state of a quantum system should contain every possible measurable quantity in that. Okay, or we can say whatever we can measure in the lab, it should be contained in this state psi, or any representation of state we want to use. Okay, so we can also say that somehow, if somehow we can find the expectation value of all the observables, this set of the expectation values of all the possible observables of a qubit, then this set should also be a valid representation for a state. Of course, it's infinite information because there are infinitely many observables. So it's the overkill. We have too much information. We don't need so much information to represent a state. This is a neater way of writing it, but this is also not wrong if it is possible to write. And an observable is a Hermitian operator, so we can write it as a mu sigma mu sum over mu from 0 to 3, where sigma 0 is identity, sigma 1 is sigma x, sigma 2 is sigma y, sigma 3 is sigma z, and a mu are real numbers for all the mu's. So this is the most general representation of a Hermitian operator. We have discussed it earlier. Since expectation value is a linear operation, arithmetic expectation value, so it will be, we can write it as a mu psi sigma mu psi. So we are getting a mu and expectation value of sigma mu. Expectation value of sigma 0, that is identity, is just 1 because our state is normalized. Okay, so it means we are left with the expectation value of A depends on sigma x expectation value, sigma y expectation value, and sigma z expectation value. This set, and of course its eigenvectors, or the a mu's, the coefficients of decomposition. So it means the set of all the expectation values is not an independent set. They depend heavily, and they depend only on these three expectation values. These are the quantities which we will get from the experiment, and a mu are the quantity in defining the observable A itself. So they are not the part of the experiment. The experimental part comes in the expectation value. So this set, we can find the minimum set which has the most information. That set will be just the expectation value, sigma x, sigma y, and sigma z. So in that way, this set of three expectation value should have same amount of information as the the state psi which we are representing, or any other representation we have for the state psi. Now let me repeat again. The first postulate says that the state of the quantum system contains all the measurable quantity or measurable information in that mathematical structure. We are just twisting this postulate around and saying that if we have somehow all the measurable information which we can measure in the lab, all the measurable information if we have in some mathematical form, that should be equivalent to the state psi. So it means, and we have reduced that whole information which is measurable in the lab to just three measurable quantities, that is sigma x expectation value, sigma y expectation value, and sigma z expectation value. So these three real numbers should be equivalent to the state psi. There should be a one-to-one relation between these measurable quantities in the lab and this state psi. And why is it so? Because this is all we can measure for a given quantum system. These three things. We can measure more, but they are dependent on these three. Now, we have to find that given a state psi, again, the state psi is given in this form cos of theta over 2, sine of theta over 2, exponential of I phi. When we perform measurement and we get sigma x, which will be sine of theta, cos of phi, sigma y will be sine of theta, sine of phi, and sigma z will be cos of theta. So these three quantities and the state psi have one-to-one correspondence. And since theta is from 0 to pi, so we can see that if we have theta and cos theta, it starts from 1, it goes to 0 at theta equals pi by 2, and it goes to minus 1 at theta equals pi. So there is no repetition in theta. So from here we can find the theta which is cos inverse of sigma z. This is unique. Once we measure the sigma z expectation value, so we can calculate the cos theta from there directly. Now, from once we have theta, then we can substitute in sine theta, and we are left with only phi, which is unknown. Now, phi has value from 0 to 2 pi. Okay, and cos theta and minus cos phi and sine phi can take positive or negative value for all those things. But we can have 10 of phi, which will be sigma y expectation value divided by sigma x expectation value. Where can be the ambiguity now? Because if we have four quadrants 1, 2, 3, 4, for the phi it is 0 to pi by 2, pi by 2 to pi to 3 pi by 2, and 3 pi by 2 to 2 pi. We have four quadrants. Tan theta is positive here, it's negative here, it's positive here, it's negative here. So if we have only the value of tan phi, then we do not know whether it belongs to even quadrants or odd quadrants. But we can see that sine theta and cos theta have different signs in all four quadrants. So in that way, by looking at the sign of sigma y and sigma z, sigma x, and the ratio of these two, we can determine where will the tan phi belong, and accordingly we can assign the value of phi. And hence, with these three quantities, we can find theta and phi, and hence we can get the state from this experimental data. Okay, so in this way, by performing measurements, we can by performing measurements and with the measured quantities, we can estimate the state psi. Okay, so one interesting thing I would like to make you see, or it's a nice observation. We have psi, which we are writing in cos theta sin theta form. We can also write it as cos of theta over 2 0 state, and exponential of I phi sine of theta over 2 1 state, where 0 and 1 are the eigenstate of sigma z, such that 0 belongs to the positive eigenstate, positive eigenvalue, and 1 belongs to minus the negative eigenvalue. Okay, so from here, if we see what is the sigma x expectation value, that will be the eigenvalue, which is 1 times the probability of 0 minus plus the eigenvalue minus 1 times the probability of 1. This is the eigenvalue times the probability, eigenvalue times the probability, and sum of all those. Right. So probability of 0 is cos square theta over 2, and probability of 1 is the mod square of this element, which will be sine square theta over 2, and minus sign comes from the eigenvalue. This is cos of theta. This is what we saw earlier, that the eigenvalue, the expectation value of sigma z is cos of theta. Now, can we, these are simple, can we do the similar thing for the expectation value of sigma x and sigma y? To do that, we need to find alpha and beta. Okay, I'm doing it for the sigma x expectation value now. Alpha plus beta minus, we are writing it, where plus is the expectation value, or the eigenstate of sigma x with plus eigenvalue, and minus is the eigenvector of sigma x with minus eigenvalue. So we can see that plus and minus can be represented in the 0 and 1 form. So plus minus is actually 0 plus minus 1 over root 2. We can also write 0 as plus minus over root 2, and 1 plus minus over root 2. So we can do this thing, and we can substitute it back in the earlier equation. Cos of theta over 2, we have 0, we write it as plus minus over root 2, plus exponential of I phi sine of theta over 2, plus minus over root 2. Now we can gather the coefficient of plus and coefficient of minus separately. Cos of theta over 2 plus exponential of I phi sine of theta over 2. These are the coefficient of plus cos of theta over 2 minus exponential of I phi sine of theta over 2 minus. So this is the decomposition. This is the representation of psi in the plus and minus, a plus minus basis. So here this is alpha, what we were saying alpha, and this is our beta. Once we have this, it's straightforward to write the expectation value of sigma x, which will be alpha mod square minus beta mod square, which will be half. We just take here the mod square of this will be cos square theta over 2 plus sine square theta over 2 plus sine theta over 2 cos theta over 2 exponential of I phi plus sine theta over 2 cos theta over 2 exponential of minus I phi minus half and the square of those. So we'll get the same term here plus same term minus same term minus same term. Okay, but the minus sign will come with just these two terms, otherwise the magnitude is same. Since there is a negative sign, when we add, these cancel and they will be twice. So there is a half factor, so we can cancel that. So we are getting sine theta over 2 cos theta over 2 exponential of I phi plus exponential of minus I phi, and that is nothing but sine of theta cos of phi. You see, we can write the state in the basis of the observable we want to find the expectation for, and then the coefficient mod square and the eigenvalue product of the coefficient mod square and the eigenvalues will give us the expectation value very easily. Similarly, we can do for sigma y. We can write it as plus y, some coefficient, gamma, plus delta minus y, where plus and minus y are the eigen vectors of sigma y with corresponding to plus and minus eigenvalues. Plus minus y written as 0, plus minus I 1 over root 2. We can write it as 0 as plus y plus minus y over root 2 and 1 as minus I times plus y minus y over root 2. We can again substitute it in psi, and we can write the psi as in the basis of sigma y, and then gamma mod square minus delta mod square will be our expectation value, and it will come out to be sine of theta sine of phi. So if we have a possibility of converting the state in the eigenbasis of the measured observable, then it will be very easy and very straightforward to calculate the expectation value of the observable. So we will be using it in a very sophisticated way, in a very nice way, when we do real state tomographies. So I would like to give an example of a state tomography. So in this example, we are taking the polarization qubits. So here we have single photons and they are in an unknown polarization state. So the state of the photon is some alpha times horizontal polarization plus beta times vertical polarization, where alpha and beta are complex number, the usual practice, and h and v are the horizontal and vertical polarization. We can, as usual, write cos of theta over 2 h plus exponential of I phi sine of theta over 2 v. Now our task is to design an experimental setup to find this alpha and beta or theta and phi. In order to do so, what we do is first we choose the basis. Choice of basis. We say the sigma z, the h and v are the eigenbases of sigma z. So it means sigma z acting on h will be h horizontal polarization, and sigma z acting on v will be minus v. So h and v are the positive and negative eigenvectors of the sigma z. So this is our choice of basis. If that is the case, then the sigma x eigenvector, which were plus and minus, will be h plus minus v over root 2. Now we know what is h plus v and what is h minus v. H plus v and h minus v are the polarization vectors along 45 degree and 135 degree. So, or we call it diagonal and anti-diagonal polarization. It is still linear polarization, but making 45 degree angle with the horizontal polarization and 135 degree angle with the horizontal polarization. So by choosing h and v as the eigenvectors of sigma z, we got the eigenvector of sigma y, and similarly eigenvector of sigma x and eigenvector of sigma y will be plus minus y, which is h plus minus I v over root 2, and they are nothing but right and left circular polarization. So let me repeat, we are choosing h and v as the eigenvectors of sigma z. That will give us the diagonal and anti-diagonal polarization states as the eigenvectors of sigma x, and right and left circular polarization as the eigenvector of sigma y. Now in the experiment, how do we find the expectation value? Our task is to find expectation value of sigma x, sigma y, and sigma z. In an experiment, how will we do that? So we basically sketch of the experimental setup will be a path in which single photons are coming one by one, and an experimental box, experimental setup which will give us 2 clicks, one corresponding to one eigenvector, and other corresponding to the other eigenvector of a given observable. Okay, this experimental setup is designed for a given observable, and these observables for us are nothing but sigma x, sigma y, and sigma z. So these state 1 and 2 will be correspondingly plus minus or plus minus y or hv. Those will be the eigenvectors. So let us do the simplest case first, that is the sigma z measurement. So we all know what is a polarizing beam splitter. A polarizing beam splitter, just drawing it with a box with a diagonal line inside it. What it does, it's an optical element, optical gadget, such that if light comes in, the horizontal light will pass through, horizontally polarized, and vertical light will be reflected. Horizontal will pass through and vertical will reflect. So we can use this polarizing beam splitter to do our sigma z measurement. We have a box, polarizing beam splitter. We send photons in state psi, and we put detectors here and here. Now we send one by one n photons in, and we get n horizontal number of photon here and v number of photon up there. Then the probability of horizontal polarization will be nh, it will be not equal but almost nh over n, and pv will be nv over n. So now we have probability of 0 state, probability of 1 state, then the expectation value sigma z will be ph minus pv. This is almost. This will be equal when n tending to infinity. So in that way, we can calculate, we can experimentally measure the expectation value of sigma z. This was the easier part. How do we perform measurement on sigma x? How do we find the expectation value of sigma x? We can always say that we can find something similar to polarizing beam splitter, which will separate diagonal and anti-diagonal states, and then we find, like we did for sigma z, we can do for sigma x. That is possible, but that will require probably some technological development, finding or developing the gadget which is similar to polarizing beam splitter. But we can do the same thing by using some smarter ways. For example, we discussed that psi we are writing as cos of theta over 2 h plus exponential of I phi sine of theta over 2 v. We can also write it as cos of theta over 2 plus exponential of I phi sine of theta over 2 plus state, or let me call it d. There is over root 2 factor plus cos of theta over 2 minus exponential of I phi sine of theta over 2 over root 2 minus a antidiagonal. So we can write psi in the diagonal and antidiagonal basis. Till now we have not done anything. Now what we can do is we can apply a unitary operator u, which can take d and a to h and v. If that is possible, then we can apply u on psi, and we get coefficient times h plus other coefficient times v instead of d and a. And then we can apply the simple polarizing beam splitter, separate h and v, and do what we did for sigma z. So what is this unitary which we have to apply, and does it not require any additional technological development? it turns out that for polarization, this unitary can be achieved by something called half wavelet. So we are not going into a detail of what is a half wave plate, but the action of a half wave plate when it is rotated by angle pi over 4, the matrix of that can be written as 1 over root 2, 1, 1, 1. Okay, so what is the benefit of this? We know that plus minus states are 1 over root 2, 1 plus minus 1. So this is same as, this is also the representation of D and A, because we are identifying D with plus and A with minus. So when we apply H pi over 4 on D, we get 1 over root 2, 1, 1, 1, minus 1, 1 over root 2, 1, 1, and we get 1, 0, which is horizontal. Similarly, if we apply H pi over 4 on A, we get 1 over root 2, 1, 1, 1, minus 1, 1 over root 2, 1, minus 1, and that is 0 and 1, which is V. So it seems like we can use H, half wave plate, to rotate to transform the diagonal and anti-diagonal bases to horizontal and vertical bases, and then we can use polarizing beam splitter to do the measurement. So our setup for sigma x measurement will look like the following. We have state psi coming, and number of them. We apply a horizontal half wave plate, sorry, not horizontal, half wave plate with rotated at pi by 4, followed by a polarizing beam splitter, followed by detectors. So NV or NH number of clicks here and V number of clicks, they will be same. This whole thing will be the setup now for sigma x, and NH will be actually ND and NV will be NA in this setup, and then we can calculate the expectation value as ND minus NA over N. Similarly, for sigma y, we know the eigenvectors are plus minus y, which is R and L. We can write the state psi as cos of theta over 2 plus I exponential of I phi sine of theta over 2 over root 2 plus y plus cos of theta over 2 minus I exponential of I phi sine of theta over 2 over root 2 minus y. We can apply operation unitary, which converts, this is R and L, sorry, this, let me write it in terms of R and L. We can find a unitary which takes R to H and L to V, and they are nothing but our quarter wave plate, again we are not discussing what is the quarter wave plate, but the action of it when it is rotated by pi by 4 angle, the representation, matrix representation of it will be 1 minus I 1. The representation for R is 1 over root 2 1 I, and representation for L is 1 over root 2 1 minus I. So Q pi over 4 acting on R will be 1 over root 2 1 minus I 1 1 I 1 over root 2, that will be 1 0, and q pi by 4 L 1 over root 2 1 minus I 1 1 over root 2 1 minus I is nothing but 0 1, that is horizontally polarized light, that's vertically polarized. So similar to sigma x, our setup will look like the following. We have states coming, then we have a quarter wave plate rotated pi by 4, followed by a polarizing wave splitter, and detectors. And our expectation value of sigma y will be p of h or r, which is same, both are same here, minus p of l, is nr minus nl over. So in that way, we can perform measurement over sigma x, sigma y, and sigma z basis, and we get calculate the probability of the clicks in the two orthogonal eigenvectors. We take the difference of that, those probabilities difference because the eigenvalues are plus 1 and minus 1. We calculate the expectation value. Once we have the expectation values, sigma x, sigma y, sigma z, then we can find the state psi, which is represented by these three. And hence we can find the value of theta and phi, and we can estimate what the state was, which was under consideration. So this is one experimental way of finding out the state of a quantum system.